Meine Damen und Herren, ich darf Sie sehr herzlich zum Gesprächsforum begrüßen, Nanotechnologie in Lebensmitteln. Welcome to the talk Nanotechnology in the Food Sector. The talks will be held in English. If you need some headsets, then behind the blue wall you will find some. My introduction will be in German, and the discussion after the two talks will also be held in German. So ask yourself if you need some headsets or not, because we wait now for some seconds so that everybody is equipped with the right language, with the right headset. Ich darf Sie nochmal ganz herzlich begrüßen. Mein Name ist Werner Bartens. Ich bin von der Süddeutschen Zeitung hier in München, leitender Redakteur im Wissenschaftsressort. Ich bin selber von der Ausbildung her Mediziner. Bei uns kommt die Nanotechnologie hauptsächlich als vage, unklare, unsicher definierte Zukunftstechnologie vor. Ich finde es daher spannend, heute zwei Vorträge unter ganz unterschiedlichen Perspektiven zu hören. Nanotechnologie in Lebensmitteln, kommt es nur auf die Größe an, does only size matter, werden wir von Professor Ralf Greiner hören. Herr Professor Greiner ist ausgebildeter Chemiker und Leiter am Max-Rubner-Institut in Karlsruhe. Er wird uns sicher viel über die Fortschritte in der Nanotechnologie, über die verschiedenen Anwendungsformen, aber ich hoffe auch über die offenen Fragen mitteilen. Der Vortrag ist etwa auf eine halbe Stunde ausgelegt. Danach haben wir einen kurzen Moment für Verständnisfragen, aber noch nicht für die Diskussion. Anschließend wird Helmut Kaiser von der Helmut Kaiser Consultancy einen Vortrag eher über die wirtschaftlichen Perspektiven, die Zukunftsaussichten der Nanotechnologie bis zum Jahr 2025 halten. Auch danach kurz Verständnisfragen. Das wird dann aber übergehen in eine allgemeine Diskussion über das Thema, bei der ich Sie auch ganz herzlich jetzt schon auffordere, teilzunehmen, Fragen zu stellen, sich einzubringen mit Ihren Punkten, Ihren Aspekten, Ihren Fragen. Ich freue mich sehr, dass Sie hier sind und darf jetzt Herrn Professor Greiner vorne ans Pult bitten.
Okay, hello everybody. So I will start a brief review about what's going on in the area of nanotechnology or nanomaterials in the food sector. The big problem we have is, first of all, definition. It's not very easy to define nanotechnology, or you have a lot of different definitions about nanotechnology and nanomaterials, especially in the food sector. And here, definition from the US, so nanotechnology involves the manipulation of matter at nanometer scales to produce new materials, structures, and devices. And the technology, let's say, it's only defined as nanotechnology if you are in dimensions in the range of 1 to 100 nanometers. So in the food area, you will see that it's very, very difficult to precisely measure the size. It's always depending on the analytical procedure you use. Then it's creating and using structures, devices, and systems that have unique properties. That's also very difficult for the food area to define what's, for example, the specific new property of a micelle. If you reduce size from 150 nanometer to 30 nanometers, is there really a new property? And the ability to control or manipulate on the atomic scale. Nanotechnology is interdisciplinary, involves physics, chemistry, biology, and engineering, and has potential impact in electronics, health, energy, material, food, and a wide variety of other application areas. What you could see in the literature is new direction in optics, electronics, and optoelectronics. Then new medical imaging and treatment technologies, and advanced materials with unique properties and high efficiency energy storage and generation. That's the most important applications of nanotechnology. And the leading commercial driver so far is electronics, but other areas are significant now and are growing in importance, like biotech, energy, or material sciences. Coming to food, if we like to define a nanomaterial, in general you say approximately 1 to 100 nanometers, or in the range of 1 to 100 nanometers. That's very difficult for regulators, because what's approximately, what's in the range of? So is 105 nanometer still a nanomaterial? Then in general you say intentionally produced. Again, it's very difficult. So if you produce a nanomaterial by classical processing techniques in food, is it intentional, like size reduction of fat globules or casein micelles during homogenization of milk? So is it intended to reduce size? In general, yes. And novel new properties or functionalities, you see I have an egg, so if you boil an egg in the morning, you modify the structure of the egg white and the egg yolk, completely different structures, and that on the nanoscale. And in general, it's intended. You want to have these kind of manipulation or changes. So by definition, you could say you are a nanotechnologist. You produce nanostructures, not necessarily nanoparticles, but nanostructures in foods. So nanoparticles are nothing new. They are naturally occurring, like viruses, bacteria, dust from deserts, volcanic ash. From established technologies or byproducts of conventional processes, you can find nanoparticles like combustion soot, paint pigments we have on the market since quite a long time, welding fumes, diesel exhaust particles, or carbon black from the photocopier toner. And some of the nanoparticles we have for a long time, like the stained glass windows, which are gold nanoparticles, steel in swords, carbon nanotubes in photographic films to find silver nanoparticles, tires, carbon black nanoparticles, paint pigments, titanium dioxide nanoparticles, and catalytic converters. You could find nanoscale coatings of platinum and palladium. So it's nothing new. If you look at size, so what we are talking about now is the size between 100 nanometers and 1 nanometer. So a virus is a little bit bigger than a classical nanomaterial or nanoparticle. A buckyball is slightly below 1 nanometer, but it's defined by regulation in the European Union as a nanoparticle. And if you look at DNA, so the whites is 2 nanometers, so a typical nanomaterial, and the titanium dioxide you already find in sunscreens. The diameter is around 35 nanometers, so also a typical nanomaterial, which is on the market, which needs to be labeled from July this year on in the European Union. If you look at the food sector, you can apply nanotechnology and nanomaterials everywhere. So in processing, so heat mass transfer, nanoscale reaction engineering, nanobiotechnology, and so on. The product, so delivery systems, there are a few on the market. Formulating food products, packaging, I think that's the biggest share of nanomaterials on the market. Food safety, nanosensors or nanotracers. Sometimes it's a bit tricky because some of them we have for a long time. So you can find literature today, a classical ELISA. So reaction of an antibody with an antigen or a protein. Today it's called a nanoscale nanosensor. Or materials, so adding nanoparticles, creating nanoemulsions, nanocomposites, nanostructured materials. So everything you can use nanotechnology. Why? why the industry is interested in nanoparticles or in nanotechnology in the food sector. So the classical approaches food industry has: improved production, improved processing techniques, improved food contact materials. They try to modify taste, texture, and sensation. They want to monitor food quality and freshness. They are working on to reduce fat and salt content in food, to enhance nutrient absorption, especially if you have bioactives, to increase bioactive absorption, and to improve traceability and security of food. To produce nanomaterials, you have, in general, two methodologies: to use mechanical or thermal energy, top-down process. We use them. You see a ball mill in our department for plant materials, for minerals. It's not that economic. You need a huge amount of energy to reduce size into the nanometer range. So it's much better to say it's sub-micro. Or bottom-up. So we use chemical reaction, cross-linking, for example, enzymatic cross-linking, chemical or physical cross-linking, or molecule self-association or self-aggregation, like the production of micelles. To me, what's very important if you look at food production. So if you use nanotechnology, so techniques which are called nanotechnologies, they result in nanoparticles, yeah, sometimes. But you could also use these kind of technologies to produce bigger particles or bigger structures. So not necessarily all technologies you summarize nanotechnologies result in the end in nanoparticles. And the other way around, nanoparticles not only derive from nanotechnologies, but you also could produce nanoparticles by conventional techniques. That's very important if you look at legislation. So in the European Union, what we try to regulate are nanomaterials and not the technology behind. If you look at food processing, you start with the raw materials. You have the techniques to process the food, and then you get the food products. If you look at the raw materials, you find naturally occurring nanostructures, not necessarily nanoparticles, structures. And during food processing, components like proteins, starches, fats undergo structural changes at the nanometer and micrometer scales. So in the food products, you have the natural occurring nanostructure plus the nanostructures induced through the processing. And if you look at the natural occurring nanostructures, you find food proteins, depending on the size. They are in between 10 and 100 nanometers size. So they are, in my opinion, true nanoparticles. In the definition, we say something about fixed boundaries, and organic molecules in general, because they are flexible, they do not have fixed boundaries. So I'm a chemist, I see it differently, but the regulators see it the other way. Structures of meat, the microfibrils are nanostructures. Polysaccharides and lipids are in general linear polymers, less than 1 nanometer in thickness, so one-dimensional nanostructures. Cellulose fibrils and plant cell walls are two-dimensional nanostructures. If you look after the processing operations, you'll find in milk fat globules of about 100 nanometer in size through homogenization, so it's a size reduction. So you produce nanoparticles, foams, two-dimensional nanostructures, so the head on a glass of beer, ice cream, whipped cream, sauces, butter, margarine. They have nanostructures, say not necessarily nanoparticles, but nanostructures. Custard and yogurt is a three-dimensional network in the nano size. See, so again, it's nothing new. Let's look about the definition of engineered nanomaterials in the food sector. So in general, we divide into nano inside, so inside the food matrix, and nano outside. So inside, it's novel food structures like nanoemulsions, food supplements like minerals. Then that's in processing nanofilters, so no nanoparticles, so nanoholes, if you want. Food analysis, the nanosensors. Food contact materials, the packaging. And in agriculture, what's going on there is they are trying to use encapsulated pesticides or herbicides. So they use nanocarrier systems with a more or less controlled release. One compound we discuss here in Germany quite often is silicon dioxide. So it's approved, it's a dietary supplement. It's used to improve technical properties of the products. So it's a nanoscale amorphous silicon dioxide, which is agglomerated. It's an anti-caking agent for powdery ingredients. It's added in a single-digit percentage, and it's used since the 60s. So in general, it's agglomerated they are agglomerated particles, so you do not find many distinct nanoparticles. But what we do not know is, do those particles deagglomerate in the stomach or in the small intestine? So do we find in our digestive tract single silicon dioxide nanoparticles? What I can say is, if you add, for example, coffee creamer with silicon dioxide to coffee, you find distinct nanoparticles in there. The other additive we discuss quite often here is titanium dioxide, a white pigment, the icing material, a flavor enhancer you use in candies, chewing gum, and so on. What you could say is that the titanium content in food is quite significant. What the colleagues didn't do is they didn't check if titanium is present there in the nanoscale range. So it's the total titanium content in the food products. If you look at the primary particles of the food-grade titanium dioxide, you see that these particles have a mean of about 100 to 120 nanometers. So it's in the nanometer range. What's on the market? Nanolycopene, BASF. So it's approved since 2009 as a novel food. The mean particle diameter is in the range of 300 nanometer. The nanoparticles are in powders or in oil, and they are added to beverages or other foods, not only for health purposes, but also for coloring. Again, very difficult if such a compound would be defined as a nanomaterial according to the legislation in the European Union. What's again on the market? Organic carrier systems for different kind of compounds like coenzyme Q10, benzoic acid, and so on. That's a product which is on the market here called Beauty Water. It contains micelles, product micelles, with a coenzyme Q10. Very difficult to analyze that you really have nano structures or nano micelles in the system. Examples of producers: Aquanova with Novasol, Neutralise, and Vesifect or Vesorb from Switzerland. So 3 companies producing this kind. So similar, not identical, but similar technologies to produce these organic carrier systems. What's in the Asian part, you find easy iron. It's an active iron. So it's a iron mineral covered with an organic cover. And so it's almost tasteless. So you do not have this iron taste. If you supplement your food, in that case milk, with iron, it's easy absorbed. In the US, you have silicon dioxide particles coated with flavor molecules, so you have a big surface area on the silicon dioxide particles, so you get an intense flavor in the mouth. You get it here on the slide. You see that it's a vanilla shake. Get it also in as a chocolate shake. And in Israel, you can find an active canola oil with phytosterols in. Similar technology, so Neutralise. There was once, I think in Australia, a bread on the market, same nanotechnology neutralise with omega-3 and omega-6 fatty acids to cover, to protect the taste, so you do not get that fishy oil taste in the mouth. The carrier system opens in the stomach or in the small intestine. Food contact materials, once on the market, are PET bottles with nanoclay in, nanosilver in food storage containers worldwide. It's on the market, not approved within the European Union. Nanosensors, nanoindicators, they are in development. I haven't seen so far that any of these nanosensors or nanoindicators are commercialized. And surfaces like antimicrobial properties, dirt and water repellent, scratch resistance for equipment in the food industry, it's in development. That's now two applications you can very often find in newspapers or in journals or on the web. Food changes color when spoiled, for example, milk. You get, let's say here, a violet color into the milk if it's spoiled. Theoretically, it's possible. Doesn't make sense for me, but theoretically, it's possible. But we need to add something else to milk, so I don't know if it's that easy from the regulation perspective to add something only to see that it's spoiled. That's the other thing, which we always discuss if we give talks about application of nanomaterials. Frozen pizza that changes its taste as a function of the microwave energy used for its preparation. So we have onions or olives or salami, egg, taste. That's an example. I think it will never exist. To break up specifically different nano carrier systems by only the small difference in the microwave energy, I don't think that it's possible. But it's a nice example you always hear if you talk about nanotechnology. Let's shift to regulation. So here in the European Union, we discuss a lot about, is there a need for nano-specific regulations in the food area? My personal opinion is no. We have sufficient regulation, and I think the existing regulation also covers the nanomaterials. But within the European Union, we started to modify some of our regulation. So we have the general food law, not nano-specific. Novel foods and novel food ingredients, there we discuss to implement nano-specific regulation issues. Food additives, already implemented. Food enzymes, already implemented. Food supplements, the same. Addition of vitamins and minerals. Food information to consumers. Food contact materials, especially plastic materials. You find nano-specific issues in there. What's the general food law says? Food shall not be placed on the market if it's unsafe. So if there's a food on the market which contains nanomaterials, then I would assume it's safe according to our existing knowledge. Because if not, we couldn't place it on the market. The problem we have in the food area is the definition. So the European Commission recommended to define nanomaterial as a natural, incidental, or manufactured material containing particles in an unbound state, or as an aggregate, or as an agglomerate, and where for 50% or more of the particles in the number size distribution, one or more external dimension is in the size range of 1 to 100 nanometer. So now everybody says, okay, then all materials which are in that size range are covered by that recommendation. Yeah, that's true. It's a definition of nanomaterial and not of engineered nanomaterial. So if you want to define what's covered by a specific regulation, you need to use a more precise definition. And the definition they used is considers only size because the European Commission thinks size is the only universally applicable, clear and measurable criterion which can be used to identify material which to their particle size may exhibit specific properties or risks. Personally, I think that's not true. We have a lot of problems to measure particle size in the food area. If you look at the market situation, so all known applications of nanotechnology or nanomaterials in food and food packaging are currently outside the EU, mainly the US, Australia, New Zealand, South Korea, Taiwan, China, and Israel. We have a reservation on the EU market. The problem we have, the market situation is unclear. We do not have a register so far. In France, we have it from this year on. There's no labeling required. In the EU, we will have labeling from December next year on. And the presence of engineered nanomaterials could not be clearly established in many food products. So to measure size, if you produce your nanomaterials, so it's a simple system, in general, it's okay. But in a food, it's very, very difficult. If you look at the discussions that the proponents say it improves shelf life, food safety and food quality, and the critics are concerned about health risks, especially that nanomaterials or nanoparticles may reach all tissues and cells, even especially those which are not accessible for larger particles. And we discussed the Trojan horse effect. So if a nanoparticle is uptaken, that it binds some might be toxic components on the surface, and they are uptaken with the nanoparticle. In general, due to the high surface area, they are highly reactive and may induce stress in cells or cell death. But so far, there's no evidence that nanomaterials are inherently hazardous. So size is not the only property which is important. So how to perform risk assessment? So EFSA says you could use the currently accepted risk assessment paradigm. So what you need to do is exposure assessment, hazard identification, hazard characterization, and risk characterization. So you say, oh, it's easy, then let's do as we always do, but we have some problems. For exposure assessment, you need to detect and characterize the nanomaterials in food and beverages. But so far, we do not have any validated methodology to do that. So if you can't perform exposure assessment, it's very difficult or it's impossible to do a risk assessment. If you look at human exposure, you have inhalative, dermal, oral. For food, oral is the most important one. And if you look at the nanomaterials, you can deliberately add engineered nanomaterials. They can migrate from food contact materials, so the processing equipment or packaging, or you might have environmental contaminants, which you find in the food. And if you look at information, we have only limited information by the industry about the use of engineered nanomaterials in the food sector. So even by looking at that knowledge, it's almost impossible to do exposure assessment. No information on migration. In general, you read always it's impossible that nanoparticles migrate from packaging material into food. And we do not have any information about the presence of engineered nanomaterials in the environment so far. So to my personal opinion, it's almost impossible to do a good exposure assessment. Hazard identification and characterization. Again, you need to detect and characterize your nanomaterials in tissues, organs, and cells. So if you do not have a methodology in hand to find your nanomaterials in a food matrix, then you do not have a method in place to find them in tissues or organs. It's even more difficult. So what you could do is, since you do not have a method in hand, then since you do not have sample preparation protocols, you can work with worst case scenario, assuming 100% absorption of your nanomaterial, and all remain as free, intact-free nanoparticles in the body. That you could do. You'll see there are some methodologies you could use for characterizing nanoparticles. So in my department, we use scanning electron microscopy or atomic force microscopy, centrifugation, filtration, then field flow fractionation and light scattering. We have laser-induced breakdown detections, and we have electroacoustic spectrometry. But even with all that equipment, we face a lot of difficulties to find the nanomaterials in the food matrix. Only to see one or a couple of problems we have, that's by colleagues. So they used, for example, titanium dioxide. So the distributor told us 5 nanometer diameter. If we use transmission electron microscopy, 16 nanometers, atomic force microscopy, 3.7 nanometers, dynamic light scattering, 660 nanometers, field flow fractionation, 2.1 nanometer. So a wide range. So I will always be asked, what's the true value? I need to say all these values are true because there are different methodologies. You measure different physical parameters, so they are all true. And that's the difficulty we have with the definition 1 to 100 nanometer, measured by this methodology. And in general, we measure everything by mass or volume distribution, and then we need to mathematically transform this distribution into a particle size distribution, and that's critical. So the algorithm, the different companies or the different distributor of equipment use is different, and we do not know the algorithm. So maybe mistakes. If you look at hazard identification, it's very difficult. Should we use the nanomaterial as produced or as tested? It's dependent on the dispersion method, on the concentration, on the experiment, on the toxicological endpoints. And different nanomaterials act by a different mechanism. So is the observed effect nanospecific? So we think that the market for nanotechnology-derived products will grow in the coming years. I told you in the beginning for which purpose. If we want to assess the products, we can only do it case by case. We know that size matters, but it's not everything. We need to look at the chemical composition, the surface properties, charge distribution, and so on, coatings. Most concern we have is over insoluble, indigestible, and biopersistent material. So not about, let's say, organic nanomaterials like micelles or liposomes or something like that. The knowledge we have, in summary, about the behavior and fate of engineered nanomaterials following oral exposure is very limited. So excretion via the intestine seems to be very efficient, but information about accumulation, metabolization, and excretion of absorbed nanomaterials is almost missing. We do not know about the capability of nanomaterials to pass natural barriers, like blood-brain barrier. And we do not have only limited data about interaction with the gut microflora, which might be extremely important if you work with nanosilver. So what we need to do, investigate the interaction and stability of engineered nanomaterials in food and feed, in the gastrointestinal tract and in biological tissues, develop and validate routine methods to detect, characterize, and quantify engineered nanomaterials in food contact materials, food and feed, and develop, improve, and validate test methodologies to assess toxicity of engineered nanomaterials, including reliability and the relevance of test methods. So, a lot to do. Only the last, transparency. As I said, we have proponents and critics, the industry and the governments, and they have different approaches to deal with nanotechnology. Let's say for us, the industry races ahead, so they bring some new products on the market. And I'm working for a governmental agency. We have difficulties to regulate the technology of the materials. In general, we lag far behind the rapid development of the new technology, as always. I think that's nothing new. But what's extremely important, we should learn that from the mistakes we did with the GMO issue. We should be open, informative, transparent in what we are doing. So everybody, the public authority, the governments, the industry, the NGOs, and the bench researchers, we should look for public engagement in all aspects of nanotechnology decision-making. Then it's easier to get this technology or the materials accepted. And to have a choice about exposure, we should label the products containing nanomaterials. In my opinion, we already started to do the same mistakes we did with GMOs. So far we have, let's say, a quite good acceptance of nanotechnology in the population, but that might change rapidly and easily in the near future. Thanks very much for listening.
Vielleicht bleiben Sie noch kurz oben. Vielen Dank, Herr Professor Greiner, für diesen interessanten Vortrag, der viele Aspekte angesprochen hat, die wir in der Diskussion vertiefen. Wenn es jetzt direkt Verständnisfragen, Bemerkungen gibt, die nichts mit einer Diskussion zu tun haben, dann melden Sie sich doch bitte jetzt. Ich sehe keine Stimmen, dann keine Finger, dann darf ich Herrn Kaiser bitten, seinen Vortrag zu halten, der aus einer deutlich anderen Perspektive sein wird.